Artificial Intelligence and Machine Learning, a comprehensive study. For the last 4 days, we have explored various fascinating domains, all starting from evolution of machine learning, evolution of artificial intelligence, and moving towards deep learning, large language models, and finally coming to quantum computing. So today we bring this program to a close, and our main focus today will be the some summary of all the lectures that are concluded in the past 4 days. So the first session will be continued by Professor Gautam Makwana, who will be talking about quantum computing for some time, followed by a session by Professor Anu Gokhale, who will be summarizing her lectures in the past 4 days, so we can refresh our memories all over again. The further schedules will be continued as a part of our assessment program, where we will be giving the presentations as already discussed in the past lectures, and also we have received a link for the test, so that is also a part of our assessment. And at the last we will be concluding this course with a valedictory session. So I hope we have an insightful day today. Let us start with this day with the session by Professor Gautam Makwana. Thank you, sir.
Okay. Good morning to everyone. This is the last day of the Gyan course on the AI and machine learning algorithm, a comprehensive study. So, in now there is a one lecture number 12. There is a uh, generative AI and the quantum computing. So it was not possible to cover the quantum computing in the lecture number 12. So I will take the about the what is the quantum computing and why we require the uh, quantum computings. So, uh, so this is my lecture number 7 regarding the quantum computing. So, in this case, I will talking about the concept of the quantum computing that include the superposition, entanglement, and interference, and the sum of the quantum gate, and how the quantum computing used in the machine learning that is known as your quantum computing learning. Now, why we require the quantum computing? So whatever we are doing the computings, that is the on the your CPU or GPUs. Okay. So what kind of the technology is used in our computing facilities? So can you tell me what kind of the technology is used for the computing technologies? How it is computing actually? Basically, what happened? It is a binary systems. Yes or no? Or whatever the information or whatever the processings are done by the binary numbers 0 and 1. Okay, that is known as your bit. Now this bit are this whatever the bit, whatever the basic gate of the digital circuit, that is the AND gate or AND gate, or are made of the transistors. Okay, and the transistor are having on the integrated circuit. So there is the CMOS technologies are used for the to make the transistor on the based on the CMOS technology. We are having the number of the or million of the transistor in a single ICs. Okay, and that will give the your power of the computer systems. Okay, so here what happened now? Can you tell me what is the clock frequency of the CPU around that? What is the clock frequency of the CPU? Around 4 to 5 gigahertz. Okay, and GPU are on the 2 or 3 gigahertz frequencies, and the smallest size of the CMOS transistor, around that it is the order of the 2 or 3 nanometers, 2 or 3 nanometer. And day by day, we are require the high computing power. And for to achieve the high computing power, we need the small transistor in the size to be fitted into the uh, to fit it into the uh, uh, into your ICs. Okay. So now after the 10 year or at the time that we require the in the below the nanometer scale, we require the transistor in your integrated circuit, or I can say CPU ICs. CPU ICs. Okay. So as for the before this one, I just acknowledge the this articles to discuss the concept about the quantum computing from the this article. Now here, so as for the this Gordon Murray, as per the your Gordon Murray in the 1975, he predicted the number of the transistor on an integrated chip double after 18 months. If it is today is the 2 nanometer, okay, so at the time after the 2 year almost, it is a number of the transistor will be the double. So in the same area of the ICs. So in this case, it is at the time it requires a very small transistor inside your IC. Okay, so this is the one reason. Okay, so whenever you go below the nanometer, at the time at the time the atom, the size of the atom, we have to create the transistors, which is not possible actually at the time the whatever the principle to operate the transistor, it is based on the classical physics mechanisms. So at the time at the very small scale, that it is fail the concept about the computing or concept about the bit will fail in the based on the physical classical principle of the classical physics. At the time that physics will not work. So at the time that we need the new physics, and that is a non-area quantum mechanisms. That is known as your quantum mechanism, or I can say quantum physics. That is the whatever the the material they use for the transistor, they are work as a at the atomic levels. So at the time, for this case, we require the different principle, and that is your quantum physics, or I can say it is a quantum mechanism to operate the binary numbers 0, 1, or it can be the transistor. So at the time, that we need the new kind of the a new kind of the physics, and that is the your quantum physics, which is work on the atomic levels of the photon and electron or neurons. Okay, so that is why we require the quantum mechanics, and the quantum mechanics are work on the three principle. One is a superposition, second is your entanglement, and the third is the interference. And based on this principle, the a bit are, or I can say computing are we have to do. That is the quantum computing. Okay, so this superposition, entanglement, and the interference. In your transistor, we are working with the making the 0 and 1, making the switch on and off, and that is the based on the your that is the based on the classical physics. Okay, now this quantum computing utilize the quantum bit, which is known as your qubit. Okay, and that which can exist in multiple state at the same time. So here in the classical computing, at a one time only one bit, only one state, either 0 and 1. But in the qubit, at the same time, there are the multiple state of the 0 and 1, or it is a combination of the 0 and 1. So that concept is that bit is known as your quantum bit. It is your qubit, and this is because of the because of the superposition principle of the your quantum mechanism. And what is the entanglement? Entanglement signifies the unique connection between the qubit, and the quantum interface can alter the outcome of the qubit. So internally, because of the interference, the state of the qubit are changed. That is a non-aerial interference. Okay, so in this case, qubit multiple state 0, 1, and the combination of the 0 and 1. So there are the multiple state in the qubit. That is because of and the using of the superposition, entanglement, and the interference principles of quantum mechanism process are used in the quantum computings. Now, what is a qubit? So this qubit is not just zero state and one state. One state. It is the superposition of the zero and one state, weighted by the complex coefficient with the probability amplitude. So here, what happened? This zero, one, and combination of the zero and one having the complex coefficients with the probability distributions, and whatever the coefficient are, if you sum up, it should be the 1. Okay, so there is a linear combination of the 0 and 1, and with the complex coefficient with the probability of the amplitude. So this is the your. Now, how we notice, what are the notation can be used. So this is the qubit is a quantum computing particles. Okay, at the level of the size of the quantum particle in the atomic level, that was a wave-like nature with a wave function psi of x, and use the notation, direct notation, like this way. Okay, this is the your notation for the qubit, and it is read at a ket psi. And another quotation, you can differentiate this symbol and this symbol, and this is read at a bra of the psi, and it is the complex conjugate transpose vector of the ket psi. So here in the classical computing, we are using the 0 and 1 state. Okay, but here in the qubit, the notation is the non-aero direct notation, and it is non-aero ket psi and the bra of the psi, ket psi and the bra of the psi. Now this symbol, this symbol is denoted the column vectors. This symbol is known as your column vector. That is the case psi, and that is the non-area ket, and bra is the from either the row vectors. So here the qubit are represented in the either one qubit in the column vector, and it may be in the row vector. So at the time it is the ket notation when it is the column vector, and it is the bra notation when it is the row vectors. So this is how we can represent the qubit into the matrix formation. The matrix representing denote the probability of the qubit to be the in the some particular state within the matrix. The topmost entry indicate the probability of the corresponding to the state 0, and the lower access the possibility of the corresponding to the state 1. So the zero bit is represented by the in the column vector 1 0, and one qubit is represented by the 0 and 1. So this first entry is having the highest probability, and it is giving the output as a 0 bit in the classical computing consideration. Now, a state of the single qubit in the direct notation and metric formation are this is the your equation, I can say, for the ket psi equal to alpha 0, ket 0 plus alpha 1, ket 1. Okay, and it is represented by the in the matrix formation alpha 0 and alpha 1, where alpha 0 and alpha 1 are the complex coefficient with the probability of distribution, with the probability of the distribution, and this coefficients, the if you square of the all this coefficient will should be the 1. Okay, so this alpha 0 square plus the alpha 1 square should be the 1. This will indicate the it is a probability distribution with the your uh, complex coefficient alpha 0 and alpha 1. And I can say the single qubit is a two-level quantum system. A two-level quantum system is a linear combination of the two basic states 0 and 1. So this is a representative of the only qubit. This is known as your qubit. That is the quantum bit in the your quantum computings. Now, in the same way, how we can represent the two qubit, the state of the qubit ket psi equal to alpha 0, ket 0 0 plus alpha 1 ket 0 1 plus alpha 2 ket 1 0 plus alpha 3 ket 1 1. So this is the how we can represent the two-bit qubit, and in the matrix notations, the two qubit are represented as a column vector. That is the ket psi alpha 0, alpha 1, alpha 2, and alpha 3, and all are the complex coefficient with the probability distribution. And if you square of this quantity, it would be the 1. So that is the representative of the two qubit for the this in the quantum computing. Now, how the 0 0 ket 0 0 is represented by the column vector 1 0 0 0, ket 0 1 0 1 0 1 1 0 0 0 1 0, and 1 1 0 0 0 1. So you can get the idea that the having the multiple state in the qubit based on the concept about the quantum computings. Now, here what happened? This is a matrix notations. Okay, it is a matrix notation. So how we get the matrix notation for the when you go for the number of the bit are increases, number of the qubit are increases. So for this case, they use the principle of the tensor product. What is the tensor product? A partial operation of the matrices to express the multiple qubit system mathematically as if M is the P across Q matrix and N is the Y cross Z matrix. Then the tensor products Mn is the P and Y cross P into Y cross Q into Z block matrix representing the multiple qubit system. So this is your, you can get the idea here. Matrix M is the P cross Q and the N is the Y cross Z. At the time the this P into Y and then cross Q into Z are the, if you do like this kind of the matrix multiplication, that is known as your tensor product. And this principle is used to represent the more number of the multiple qubit quantum systems. So this is a just example here. Let M equal to this 2 by 2 matrix and N is a 2 by 2 matrix A11 and A12 like this way. And this is the notation of the tensor products M plus N or M and the N tensor product. So here what happened? This is your P into Y. So this is the A1 into the Y. That is your B1 and B21. So you can get the A11 B11, then A11 B12, and then it is a A21 and the B11 A12 B12. So this is a idea about the tensor product of the matrix. So you are familiar with the matrix multiplications, row and the column wise matrix multiplication, but this is the difference product, that is the non-ideal tensor product. It is a P into Y cross Q into Z. So here it is showing the like this way. This is a 2 by 2 M and N. This can be represented by the 4 by 4 matrix like this way. So here the multiplication is less. Now in the machine learning or in the whenever it is a high dimensional operations, at the time the instead of the matrix multiplications, they are following the tensor product in the machine learning computation, where the number of the operation will be the race, and you will get the dimensional reductions in the machine learning or deep learning algorithms. Whenever we are talking about the large scale model or in the generative AI, they use this tensor product to get the more whenever we require the dimensional reduction. And this concept is used also in the quantum computing. So here it is the cat 0 and the cat 0 tensor product is represented by the cat 0 0 tensor product is represented by the 0 1, and 1 0 is represented by the 1 0. So this is the idea about the how the tensor product of the one bit column vectors. So it is a one bit. This is the what do you call two cross one column vector, and this is also the two cross one column vector. So this can be represented by the this cat 0 2 bit two qubit are we can achieve the matrix representation for the any number of the qubit. Okay, so this is this idea how this tensor product is happen. Zero tensor product cat sorry cat 0 and the cat 0. It is 1 0, then tensor notation, and 1 0. It is giving the this 4 cross 1 column vectors, which is represented by the 0 0 cat 0 zeros. Now, this is the one another concept which is not in the case of the classical computings. Okay, so this is non-radio block sphere represented of the qubit. So here it is a because it is a complex coefficient alpha 0 and alpha 1 complex coefficient with the probability distributions. Okay, so this the bit can be represented into the this is non-area block sphere. Okay, so this is your z, x, and y axis, and this is your imaginary axis and the real axis. So like uh, uh, based on the superposition, based on the entanglement, and based on the interference, there should be the change in the probability distribution in the complex numbers, and this can be represented by the phi and the thetas. Okay, so this is one kind of the how we represented the qubit in the sphere. Okay, so this is the cat 0 and the cat 1. So like this way, this is a representative of the how it can be represented the state 0 in the single qubit. So this is representative of the 0 bit, and this is the representative of the 1 bit, and this is the this figure will represent the superposition of the 0 and 1, superposition of the 0 and 1 like this way. So what is the superposition here? Which enable the qubit to exist in a combination of the state. Upon the measurement, the superposition collapse, and the final outcome is determined depending on the probability distribution of the qubit state. Quantum superposition is the ability of the qubit to be multiple state simultaneously until it is measured. Okay, so this is your superposition is a linear combination of a state 0 and state 1, and that is known as your superpositions. Now, in the same way, the how it's represented the cat 1. So cat 1 is represented by the this red line. Okay, at the same way, cat minus is represented by the 1 by 2, 1 and minus 1 in the column vector. It is represented like this way. And the cat gamma, it is the point in the matrix notation. It is 0.8137 plus 0 I plus 0 plus 0.5812 I. So this is a case about the how it can be represented in the block spheres. Okay, so this is how we can represent the state of the qubit into the block sphere. and this is one of fundamental concept. There is a difference between the classical computing and the quantum computing. Zero and one state in the classical computing, and the zero and one state in the quantum computing. Now, what is a quantum entanglement? Okay, the probability of the qubit state can be affected by the chain of the another qubit state probability. This phenomena is called as a entanglement, which is not happen in the classical computing. So here a zero bit in the classical computing, zero bit and one bit. So there is a independent state. Okay, and there is no dependency of the zero bit. The output of the one bit is not depend upon the another state of the bit. There is some interference or some kind of the dependency on the one atom with the another atoms in the classical physics. Okay, but it is occur whenever the both the atom are very nearby. Suppose both the electron are very nearby, then there is a dependency of the one electron with the nearby electrons. Okay, so it is whenever the distance between the two electrons are very small in the order of the micrometers, or it is in the less than the micrometer, then there is a dependency of the electron with the nearby electrons in the classical physics. But in the quantum physics, if the particle, or I can say a quantum particle, are very far away, then there is a possibility of the dependency between the one particle and the second particle, which is very far away. And this is because of the dependency, and that is known as your entanglement. That is known as your entanglement. There is a dependency of the one quantum particle with the another particle, and that will use to change the state of the qubit, and that is known as your entanglement. So regardless of the physical distance between the entanglement qubit, a change in one qubit state probability can change the probability distribution of all qubit in the entangled quantum system. Okay, so whenever the one state will change, at the time the other state of the qubit also change, which is not happening in the classical computings or classical physics. That is a difference into the quantum physics or quantum mechanisms. Okay, so that is known as your quantum entanglement. Okay, in quantum circuit, entanglement is created through the quantum gate by performing the specific operation on the qubit, then result in the inseparable state of the qubit. Okay, so this is a just diagram of the whenever there is no qubit. There is no qubit at the time that this state are independent with the this state, and this figure will indicate the quantum state are entangled. If you change the probability of the this state, at the time it will change the this state of the this bit, this qubit. Okay, so there is a dependency, and this is known as your qubit. The chain of the probability of the this state will change the state of the this bit qubit also, and that is known as your entangle. So there are the different notation: ket psi 1 by 2, ket 0 plus, ket 1 and ket 1. Psi prime, the ket psi prime is equal to 1 by 2 0 0 minus ket 1 and ket 1. Like this way, we can get the many other state in the entanglement, which is known as your Bell state, which is known as your Bell state, or it is known as your Einstein Podolsky Rosen ELP pair. That is your specific state in the qubit system. So this is the what the if there is a change in the probability of the one state, the other state of the qubit will also change. That is known as your entanglement, irrespective of the distance between the qubit, which is not happening in the classical computing. Now, what is a quantum interference? So now, in the quantum article, okay, shape, it can be represented as a quantum waveform. So qubit is a like a one way. I can say it is a wave-like nature. Qubit is a wave-like nature. So this is wave-like nature is the state 0, 1 and the superposition of the 0 and 1. So this is a one kind of the quantum waveforms. In reality, the qubit has a wave-like nature that is described by the quantum waveform satisfy the conjugal equation as shown in the figure. The waveform describes the quantum state that consists of the complex probability amplitude and the corresponding probability of the quantum system state. The value of this quantum waveform is depend upon the probabilities distribution of the state and the and this is called your quantum interference. In the multiple qubit, the waveform are added together or to give an overall waveform, wave function describing the resultant state of the quantum system. This adding process is called a interference. Okay, so multiple qubit state are adding, and that is known as the interference. So this is your kind of the two qubit. Okay, it may be during the addition. It may be either destructive interference or it may be the constructive interference. And this is the this is the result of the adding the two uh, quantum waveforms. Okay, so this is known as your interference, either constructively or destructively, and affect the probability distribution. It is a fundamental phenomena that arises from the wave-like nature of the quantum particle, such as the electron and photon, and its distinguished quantum system from the classical system. The interference is a foundational concept in the quantum computing, allowing the quantum system to perform the computational by updating the probability distribution of the quantum state. Now this is your just idea. What is the qubit? Okay, and what are the principle behind quantum computing, a quantum mechanism? That is the superposition, interference, and the entanglement. Superposition is the just uh, linear combination of the state, and the interference is the adding the waveforms either constructively or destructively, and the entanglement is the dependency of the two state based on the when the probability distribution is changed, then the state of the qubit will change. Okay, so now how the gate are quantum gate. What are the quantum gate which is used for the develop the quantum processors? Okay, in the digital circuit, we are having the basic gate, AND gate, NOT gate, OR gate. Okay, like this way there are the quantum gate. So one is the identity gate does not modify the state of the qubit, does not modify the state of the qubit. It is evolutionary matrix. The notation, the matrix representation is given by the I equal to 1, 0 and 0, 1. And this is your notation of the identity gate where the state of the qubit are not modifying. Okay, and the single qubit polygate are x, y, z are based on the poly matrix sigma x, sigma y, and sigma z, which are useful to modify the state of the phase of the qubit. So this single qubit polygate are having the identify the poly matrix and useful to modify the state of phase of the qubit. So this is the poly x gate, poly y gate, and poly z gate, and this is your notation of the poly x, poly y gate, and poly z gate. The poly x gate is the quantum equivalent of the NOT gate. Okay, and for the classical computer, it map 0 to 1 and 1 to 0, called the qubit trip gate. Poly y gate 0 to complex ket 0 to ket 1 and 1 to ket 0 in the conjugate. Poly jet gate will be the 1 to 0, 1 to minus 1 and leave the state to 0 unchanged for the phase shift. It is the 180 phase shift of the state. Okay. At the same way, single qubit phase shift gate. So this is your T gate. Introduce a phase shift to the quantum state of the qubit. T equal to T gate P of the pi by 4. So it will introduce the phase shift of the pi by 4. And this is the notation. And pi by 2 phase shift non-radio S gate. And this is your notation for the Z. It is a phase shift of the pi. At the same way, another a single qubit is a Hadamard gate. Create the superposition state with the equal probability distribution for a given qubit. So H equal to in the matrix formation by this way, and notation is for this gate, Hadamard gate is this one, and it's mapped like the 0 bit. Gate 0 is a gate 0 plus 1 divided by root 2, and gate 1 is equal to gate 0 minus gate 1 divided by root 2. At the same way, two qubit control gate. Two qubit control gate is a two qubit gate where the first qubit acts as a control and the second qubit as a your target bit. So it is the one is the control bit and second is the target bit. And this is your notation of the 2-bit control gate, which is known as your C node, and this is your symbols. So control node gate, also known as your control X gate, operating on the 2 qubit, perform the node operation on the second qubit only when the first qubit, which is the control qubit, is a gate 1. Otherwise, leave the second qubit unchanged. And this control bit, the control gate can be generalized using the universal matrix U given by this, and that is the control U gate, which is the CU gate, where the universal matrix is putting here. So depending upon this universal gate, there are the many other type of the control gate. Okay, so this is your control X gate, and at the same way, this is the control Y and control Z gate, which is the CY and the CZ. Now, in the same way, 2 qubit swap gate. Uh, 2 qubit swap gate is to perform the swap operation between the 2 qubit. It is a fundamental quantum gate used in the quantum computing with the primary purpose of the exchanging the state of the qubit. And this is your notation. Qubit 1 and qubit 2 swap. It is after this operation, it is swapping the qubit, and this is the notation, and this is your symbol of the swap 2 qubit swap gate. At the same way, a 3-state qubit, that is known as a Toffoli gate, which is the CC node gate, control node gate. The Toffoli gate is named after the Tommaso Toffoli, and it is also known as your control node gate, or it is a Dicey gate D pi by 2. Toffoli gate has 2 control bit and 1 target bit, and based on this, the target qubit will be inverted if the first and the second control bit are the gate 1. Okay, so this is a representative of the Toffoli gate with the 3-state qubit. Now, whenever you do the quantum computing, measurement of the state of the quantum computing, so in the quantum computing, the measurement is a fundamental operation that provide a way to extract the information from the quantum system. When the quantum measurement is performed on a qubit, it yields a classical result. The measurement outcome corrects the superposition state of the qubit and provide either 0 and 1 based on the probability distribution of the Q state. And the measurement provide the information about the quantum state of the qubit at the time of the measurement, and measurement convert the multiple superposition probability state to the one absolute state and correct the state and superposition. The measurement of the qubit is quite complex as compared to the classical computing measurement of the state. Okay, so I will not put into this one. This is a simple quantum basic quantum circuit. Okay, So this is your X gate. Input is a gate A 10, and output is a gate A. It is a 0 1. So it is a inverted. Okay. So this is the just a matrix formulation for the how we get the in the classical computing classical digital circuit and all logical operation we are performing. Okay, but here it is a tensor product of in the matrix formation that we have to perform here to get the your output of the quantum circuit. Okay, and that is based on the probability and based on the interference and based on the entanglement. So these are some of the example of the how the basic quantum circuit are created. Now, what is the quantum machine learning here? Okay, so here it is a machine learning and the quantum computing. Both are the different phenomena. And if you combine the concept about the quantum computing and with the machine learning, that is known as your quantum machine learnings. So here there are the many algorithms. There is Joda algorithm, which is involved determining the whether a given Boolean function is a balanced or constant in a single step. In a single step. So in the classical computing, it will take the more number of the step, but the same thing can be done in the single step. That will increase the high computing capability of the your processing because of the quantum mechanism, providing a significant speed up compared to the classical algorithm. At the same way, a Bernstein Vajirani algorithm is used to find a hidden binary string in a function with a fewer query as compared to the classical algorithm, even in the presence of the noise and imperfect quantum devices. Simon algorithm is used to obtain the period of the vectorial Boolean function with the polynomial time complexity with the exponential speed up over the classical algorithm, and it is used for the autocorrelation spectrum and the vast spectrum of the Boolean function. One of the popular algorithm in the quantum computing are the SOR and the global algorithm is used to SOR algorithm is used for the to find the prime factor of an integer by using the superposition and the entanglement to perform the factorization process exponential faster than the classical algorithm, and global algorithm is used to find the specific value within the unsorted and unstructured database or list exponentially faster than the classical algorithm. And first generation, the evolution of the quantum machine learnings. Okay, first generation of the quantum machine learning use of the quantum computer in machine learning to speed up the linear algebra operation exponentially as the state space grows. Use of the solving a linear equation for classification problem such as a perceptron or linear regression. And the second generation of the quantum machine learning is with the advent of the NISQ. NISQ is a noise intermediate state quantum processor. Okay, this NISQ processor are having the less than the 100 qubit gate. Okay, that is the NISQ processor. That this QML utilize the parameterized quantum circuit and quantum neural networks in deep learning application. QNN parameters are optimized with respect to the cost function through the black box optimization or gradient-based method for learning of the data machine. In the hybrid quantum machine learning, it is the use of the combination of the classical computing and the quantum computing. So, okay, so this is a classical computing and this is your quantum computing. And use of this is known as your hybrid quantum machine learnings. Now, these are the some of the well-established quantum machine learning algorithm: quantum SVM, QNN, QCNN, QLSTM, QRBF-NN, QGAN, quantum price level, quantum autoencoder, and quantum K-means. which are the a few of the basic machine learning and the deep learning algorithm, and there are the different kind of the purposes for the different kind of the quantum machine learning algorithm, and it is noted the category and the purpose of the this ones. So this quantum auto encoder, for example, quantum auto encoder used for the compresses and the reconstructs the data. So here, basic idea is the yes, compared to the classical computing facility, the quantum computing will speed up the operations in the processing. It will give the fast processing with the grow in the exponential growth. So that is the algorithm, and these are the just few simulators. Quantum simulator, QIS, KIT, AER, QITIP Quantum Toolbox in the Python, and the CRQ. It is the open source interface designed for programming the quantum computers. Okay, so there are the different kind of the quantum simulator, and the project Q. So it is the open source programming interface for the quantum computer, support the comparison framework for the various type of the quantum hardware, such as the IBM quantum experience chip, Azure quantum, AWS bracket, AQT devices, all it is the iron-trap quantum devices, indicate for the testing and the debugging the quantum algorithms. And then PyQL, it is the Python library for writing the quantum programs using the Quill and the quantum instruction language developed by the Rigetti Computing Incorporation. Is come with the quantum virtual machine for simulating and just testing the quantum circuit. So this is just idea about the what is the quantum computing, what are the quantum gate, and what is the quantum machine learning, and what are the simulator that is in this lecture. Any question? Okay, thank you. Now this is I just want to say India is launched the quantum machines. Okay, and this is a requirement of the next generations. Okay, so this is just given the basic idea about the quantum computing, and India need the contribution from the youngster to give the novel quantum computing facility either in the various domain of the quantum computing. Quantum computing are having the three domain. One is the quantum computing, one is the quantum communications, and a third is the quantum memories. Okay, memory, and for this case we need the different technologies for the chip manufacturer, different algorithm, different communication between the 2 point with the reliable and low latency in the order of the microseconds. That is a requirement in the quantum computing. Okay, okay, thank you. Now, one more thing is we have opened up the test. Okay, already it is given in your email. So we are giving the best 3 attempt, and before the 2 p.m. you have to finish, and you have to sit here only. Huh? Don't go anywhere. Okay? Huh? Okay, very good.
I think most of them have completed already.
Okay, okay, okay. Then okay. Okay, okay.
Okay, so thank you, sir, for such an invoking session. Now let us welcome Professor Anu Gokhale for our final presentation by their side, and then it will be our turn. So best of luck, everyone.